Hey everyone, welcome to our last lesson of the week. Today we're going to talk about another topic that you have seen in Algebra 2, and we're just going to review it in this class. Okay, so today's topic is transformations. Aim is how do we graph transformations of functions. Homework is in the OpenStax textbook, page 85, numbers 11 to 19 odd. So these odd problems here. So 11, 13, 15, 17, 19. And then move on to page 86 and complete numbers 33 to 35. And then lastly, page 88, and again, 53 to 61 odd. So just really quickly as I guess, an announcement, right? So if you haven't realized already, there are odd answers in the back of this textbook, so you can check your answers. Please do so because it's a great way to, adjust, see if you got the correct answer, and then if you didn't, that's okay, right? Just see where you went wrong and learn from that, right? So I encourage you to please check your answers in the back, and I'm intentionally assigning the odd answers just so that you can see, like immediately, if you did your work correctly, okay? So yeah, please do that. Great resource in the back of the textbook. And I'm actually going to read the objectives today. I know I haven't done usually in the past, but yeah, I think it's good that we do so. So let me read it for you. So one of the first objectives of today is graph appropriate transformations. So translations, reflections, stretches, shrinks of functions given the parent function. Okay, in the textbook, you're actually going to see a different word. And let me share the textbook actually. And this is actually a preview of the homework. Okay, so they're going to use this word toolkit functions. So by toolkit functions, don't make too much of it. It's just a function that you're already familiar with. So with regards to our questions on the homework, right? So these are some questions on the homework. So this, for example, is just a translation of x squared, right? And this is a translation of the absolute value function. This is a translation of square root of x. All right, so just note that here. Okay, so square root of x, right, x squared, and absolute value of x. I mean, there is a list of these functions that they mean, when they say toolkit functions. But I won't stress that here because these are already stuff that we know. But yeah, just be mindful that that's what they mean when they say toolkit functions. Okay. All right, back to the lesson. And then the second objective is describe how a parent function is transformed given the equation. Okay. All right. So those are two objectives. Your do now for today is actually a review of yesterday's topic, which was average rate of change. So let me jump to that slide here. All right, here it is. Okay, so for the function f of x equals x minus 3 squared, whose graph is shown below, find the average rate of change between the following points. Part A is x equals 1 and x equals 3. Part B is x equals 4 and x equals 7. So 1, 3 is shown here. 4, 7 also shown here. Okay, so here we can actually see that the slope is supposed to be negative, right? So we can keep that in mind when we're getting our answer. And then here, the slope is supposed to be positive, okay, because it's sloping up. All right, with that said, though, let me get to the solution. All right, so average rate of change, as we know, it's f of b minus f of a over b minus a. So f of 3 minus f of 1 over 3 minus 1. So f of 3, if you plug that in here, right, you're going to get, right, 3 minus 3 squared, that's 0, right, which is what you see here. And then next we have f of 1, so 1 minus 3 squared, that's 4, right? That's negative 2 squared, that's 4. So you get 0 minus 4 in the numerator, divide that by 2, right? 3 minus 1 is 2. You're going to end up with negative 2, which is negative as we expect. Next, we have f of 7 and f of 4. So if you plug in 7 into the function, you get 7 minus 3 squared, and then 4 into the function, you get 4 minus 3 squared. So 7 minus 3 is 4, 4 squared is 16, which is what you see there. And then 4 minus 3 is 1, 1 squared is 1. Okay, and then 7 minus 4 in the denominator, which comes out to 3. You're going to get 15 divided by 3, which is 5. And that's positive as we expect. Follow-up question to that. Explain why these average rates of change are different as opposed to yesterday's example of d of t equals 3t plus 2. So another major concept that we talked about yesterday is f of x equals x minus 3 squared is not a linear equation, right? It's parabolic. So as d of t equals 3t plus 2 is, and therefore does not have a constant slope, right? So that was the concept I harped on yesterday, right? When you think of slope, I want you to think of line. When you hear average rate of change, I want you to think of other functions, right? Because most other functions have their slope that have a slope that varies throughout the function, right? So as we can see here, the slope is negative. Here it changes to something that's positive, right? But for a line, that's not the case. The slope for this line is always going to be 3. Okay. All right, with that being said, though, let me get to the topic for today, which is transformations. This is just going to be a hodgepodge of the various transformations that you've seen last year. And so it'll just be pretty much a review. Hopefully it seems familiar to you. Okay. So actually, let me get to the slides. Let me show you the overview first. Here, we're going to first talk about vertical shifts and then horizontal shifts. Next, that's followed by combining horizontal vertical shifts, reflections, vertical stretching and shrinking, and the last thing is horizontal stretching and shrinking. And then in closing, we'll solve a question together. So here's a slide. So vertical shifting, okay? So sketch the graphs of the following 3 functions. So we have x squared, right? And I'm just going to show you the answers here. So these should be just quick, you know, x squared plus 3, x squared minus 2. And as you remember, hopefully, right, this shifts 3 units up, and then this shifts 2 units down. All right, so vertical shifts, it's pretty intuitive, right? If you have plus, you go up. If you have, if you're subtracting something, you go down. Okay, so in summary, assuming c is greater than 0, right, assuming it's positive, to graph f of x plus c, shift the graph y equals f of x upward c units. To graph f of x minus c, shift the graph of y equals f of x downward c units. Okay, pretty intuitive. If you need to copy this, please pause the video here. Otherwise, I'll move on to the next section. Okay. All right, next topic is horizontal shifts. So sketch the graphs of the following 3 functions. We have x squared, x plus 4 squared, x minus 2 squared. Okay, so this is our parent function, or as our new textbook calls it, the toolkit function. So we have x squared here, vertex at the origin, right? So plus 4. So horizontal transformations are actually counterintuitive. So vertical transformations are intuitive, whereas horizontal is counterintuitive. Okay, so vertical, intuitive, horizontal is counterintuitive. So plus 4, it actually moves to the left. Okay, you might think that it moves to the right because, you know, there's a positive x-axis, right? But it's actually the other way around. And I'm not going to get into like the details of that. It's not really that interesting. But that's just the way it turns out. And we have x minus 2 squared here, which moves to the right. And I'll give you a mnemonic in just a bit on how to memorize this or how to remember it. Okay. But this is a summary here. So assuming c is greater than 0, and yeah, that's the mnemonic here. It's a FedEx logo, but I'll explain it in a sec. Assuming c is greater than 0, to graph f of x minus c, shift the graph y equals f of x to the right c units. So if it's minus, it's to the right. And f of x plus c, shift the graph y equals f of x to the left c units. Okay, so just like that Beyonce song, to the left, everything you know in a box to the left. Okay, so plus c, left c units. Okay, now as promised, let me explain this logo. So I remember when I was learning this back at Mystery High School, to remember this horizontal transformation, I actually remembered. So this is something pretty random. I think my 5th grade teacher was the one who told me that there's a hidden arrow in the FedEx logo. Okay, right here. Okay, so if you don't know, now you know. There's a hidden arrow right here, and luckily for us, it actually kind of looks like a minus sign. So if you just take this part, the rectangular part here, it kind of looks like a minus sign, right? So when you see this minus sign, right, x minus c, think of this FedEx arrow, right? So minus means that it moves to the right, right? And as we see here, the FedEx arrow is pointing to the right. Okay. All right. But yeah, feel free to use or not use that mnemonic. But yeah, that's how I ended up remembering it. If you need to copy this summary, please pause the video here. Otherwise, I'll keep moving. Okay. Actually, just a quick word regarding these transformations. So another important thing to know is identifying horizontal and vertical. So if it's horizontal, you'll see that the number is kind of attached to the x variable, right? So it's x plus 4, that entire thing squared. Whereas the vertical transformation, the number is outside, right? So actually, let me show you this. So x squared plus 3, right? The number is outside of x squared. Okay, so the vertical transformations, the number is like outside and disattached, I guess you could say. And for the horizontal transformations, the number is attached to the variable. Okay. All right. Let me move on to the next thing. So this is just a quick example regarding what we just talked about. Starting with the graph of y equals square root of x, sketch the graph of f of x equals square root of x minus 3 plus 4. And as you can see, you can actually see the answer here. You have square root of x, which is this function here in black, right? And then to transform this, we're first going to apply the horizontal transformation because that's closer to the x variable. So remember, minus means we shift to the right. So right 3 units, that's this in blue. And then lastly, we will shift up 4 units. Okay, so 1, 2, 3, 4. So this graph in pink is our final answer. Okay, so right 3, up 4. Okay, and this will be similar to one of the homework questions, or maybe a few of the questions that you'll see on homework tonight. All right. All right, next we'll talk about reflections. So reflecting graphs. Suppose that we know that the graph of y equals f of x. How do we use it to obtain the graph of y equals negative f of x? And try sketching the graphs of y equals x squared and y equals negative x squared. And how do we use it to obtain the value of y equals f of negative x? Try sketching the graphs of square root of x and square root of negative x. Okay. For this, I know you see the summary here, but let me show you the graphs. I'll use the graph calculator emulator. Just to make sure. Okay, yeah, there we go. Okay, so the first graph is x squared, and yeah, this is just the parabola, right? And then we have negative x squared. Okay, and this is going to be a reflection, as you'll see, over the x-axis. So it's going to flip over like that. So pretty intuitive, right? Something that we've seen a lot of times before. Okay, so in other words, that'll be a reflection over the x-axis, right? We're flipping this across this line right here. Okay, the other graphs in question were square root of x, so square root of x, and then square root of negative x. Okay, and you'll see that this is a reflection over the y-axis. Okay, so this is our normal graph, and this is the transformed graph. Okay, reflected over the y-axis, this vertical line right here, right? All right, so to summarize that, the graph y equals negative f of x, reflect the graph y equals f of x in the x-axis. So reflect that over the x-axis. And to graph y equals f of negative x, reflect the graph in the y-axis. You can say in or over, right? But actually, I would just imagine like these graphs. So whenever you, in case you forget, right, just try graphing them, right? So if you graph x squared and negative x squared, you'll see that it reflects over the x-axis. And then for the other one, it's square root of x and square root of negative x. You'll see that it reflects over the y-axis. But if you need to copy this, please pause the video here. Otherwise, I'll keep moving. Okay. Lastly, we have vertical stretching and shrinking, and then that's followed by horizontal stretching and shrinking. So we have f of x squared, f of x equals x squared, I should say. To sketch a graph of each of the following two functions, we'll sketch 3x squared and 1/3 x squared. Okay, so these are graphs from the textbook, our old textbook. So we have x squared in black here, and then we have 3x squared in pink, so right here, and then in blue we have 1/3 x squared. Okay, so as you could could reason, right? So 3x squared, that's going to be stretched up because each y value is tripled, right? So if we take this y value here of 1, 1, then that gets mapped to 1, 3 now, right? That goes over here. But for 1/3, it's going to be it's going to decrease. Okay, so 1, 1 would go now to 1, 1/3. Okay, and so that's pretty intuitive. And to summarize that, to graph C, well, I should say, sorry about that. To graph y equals C of f of x, right? So if you have C is greater than 1, right? So in this case, we had 3x squared, right? It's greater than 1. Stretch the graph of y equals f of x vertically. So stretch it up, right? Just like you're physically stretching, right? Vertically by a factor of C. If it's a fraction, so if it's between 0 and 1, that means it's a fraction. Shrink the graph of y equals f of x vertically. So shrink it by a factor of C. Okay, so shrink it by a factor of 1/3 in this case. Stretch it by a factor of 3 in that case. All right, if you need to copy this, please pause the video here. Otherwise, I'll move on to the next transformation. All right, lastly, we have horizontal stretching and shrinking. So we have this graph here. Let me change that to equation. Sketch graphs of the following two functions, so f of 2x and f of 1/2 x. So I actually don't expect you to draw this out. Let me just show you what it is. So f of 2x is going to be, it's going to move quote unquote faster, more quickly, right? So as you can see, there's like more oscillations, whereas f of 1/2 x, it moves more slowly. It gets stretched out, right? And I know that they didn't show that here, didn't show this graph here, but I think the best way to remember this rule is to just think about the trig functions, right? So I think the reason why they didn't show this here is because trig is introduced later in this book. But since we have learned trig before last year in Algebra 2, trig, let's just use that graph, right? So I'm going to go back to the calculator, and then let me graph. So I'll first graph sine of 2x, and then sine of x. Okay, and you'll see that sine of 2x moves more quickly, right? And if you remember, right, the period of the sine graph is 2 pi divided by this coefficient here. So 2 pi divided by 2, that's just pi, right? So it completes a cycle in half the time. And let me zoom in because it's hard to see. All right, let me see if z trig works first. Okay, there we go. So this is sine of 2x, right? And you'll see that sine of x, this graph that's coming up right now, moves slowly, right? Okay, so sine of 2x moves more quickly. Okay, and let me replace this one with sine of half x. So I'll just write 0.5x, and you'll see that this moves more slowly. Okay, this is stretched out, right? And this is this graph right here is sine of x, right? Okay, so as you can see, sine of half x moves more slowly. Right there, the period would be 2 pi divided by that coefficient. So 2 pi divided by 1/2, that's 2 pi times the reciprocal of 1/2, which is 2 pi times 2, which is 4 pi. Okay, so it moves half as quickly, so to speak. Okay, But yeah, that's how I would remember this. So I'll just think of the trig functions, right? And period. Okay, but to summarize, to graph, okay, so graph y equals f of c of x. So as you can see, the coefficient is right in front of x, so it's attached to the x variable, just like the horizontal translations. The number is attached to the variable, right? So this is a horizontal stretch or shrink, right? So if c is greater than 1, so in our example, let's think of sine of 2x, right? Shrink the graph, so it's going to move more quickly, right? So I know this is not sine of 2x, but it has the same transformation, right? So it gets shrunk, it gets pushed in, right? You shrink the graph horizontally by a factor of the reciprocal. Okay, so you shrink it by a factor of 1/2. Okay, so you have it, right? In the example of our sine graph, right? The yeah, so the area, right? Or I guess it gets pushed in by a factor of 1/2, and it moves more quickly, right? It doubles the speed. Now, if it's a fraction, so if it's between 0 and 1, then you stretch it out, right? So it moves more slowly. So note that stretching it out horizontally means that it moves more slowly, right? So you stretch it out. Okay, so stretch the graph horizontally by a factor of 1 over c. So in the case of our sine graph, that's 1 divided by 1/2, so that's 2. So stretch it out by a factor of 2. So you kind of double the uh, range. I don't want to use that word range because that means other things, as we know, but it doubles the span of the graph. Okay, but regardless, please pause the video here if you need to copy this down. Okay, otherwise I'll move on to our last thing for today, which is the classwork question. Okay. All right, and yeah, just note here that today we actually don't have a worksheet, so it's just this question. So in class, this lesson was kind of long, so I wouldn't normally have a worksheet. So we're just going to solve this together right here. Okay, so we're going to sketch the graph of the function f of x equals 1 minus 2 times x minus 3 squared without using a calculator. Okay, just using our knowledge of transformations. And let me just show you the answer. Okay, well, if you want to try it on your own, pause it here. But if not, I'll go on to the solution. Now, let me just preface this by saying you don't have to know the order. So the pre-calc teachers, we're not going to test you on the order of transformations. There actually is an order that we should follow, but yeah, we're not going to emphasize that here in this class. Okay. Actually, I explained it up in the lesson plan, so let me go there. Okay, here we are. Okay. Well, this is the solution from the textbook. So starting with the graph of y equals x squared, we first shift to the right 3 units. Okay, so that's this part here, x minus 3. So shift right 3 units, right? That FedEx arrow moves to the right 3. To get the graph of y equals x minus 3 squared, so initially we have this parent function or this toolkit function, y equals x squared. We first shift to the purple one, x minus 3 squared. And then we reflect in the x-axis and stretch by a factor of 2 to get the graph of y equals negative 2 x minus 3 squared. Okay. Well, as you can see, so for the ordering, we move inside out, right? So we first start with this, and then we move outwards to that. Okay, so we reflect and then stretch by a factor of 2 to get this graph. That's the graph in blue here. Okay. Yeah, so we reflect over the x-axis and stretch. So stretch upwards, so all the y values are going to double. And then lastly, we shift upward 1 unit to get the final graph, which is in pink here. And that's this graph here, 1 minus 2 times x minus 3 squared. Okay, so the pink graph, that should be your final answer for this question. Okay. If you need to copy this, please pause the video here. But that's all I want to say for today. And I'll see you all in the next lesson. Have a great rest of the day.